Hi, we are going to take a look today at the activity Analyzing Piecewise Functions. This is a fantastic activity to do within the area unit because it calls on students to remember their knowledge of basic area formulas for area of a circle, triangle, trapezoid, rectangle, and it also allows them to spiral back in and apply the information that they learned in the transformations units regarding reflections and translations up and down in order to combine the two so that you have a greater concept of how you can determine things such as area without having to actually calculate it, but using a foundation of transformations in order to determine those things. So let's take a look at what our graph looks like. The first thing that we need to discuss is the fact that this says y is equal to f of x. For some of your students, they may not have taken the accelerated courses within middle school. They may not be familiar very much with this notation f of x. So this may require just a small introduction, but nothing that you want to get too deep with. You can deal with this introduction using the table and the graph. So our first question that we want to talk about is, let's classify what each of these figures are. We have a semicircle, an isosceles triangle, and a trapezoid. I generally ask my students to do those first 5 problems. We pause, we take a moment to review our solutions, and then we can move forward. So take a moment now, pause the video, work 1 through 5, and when you're ready to come back, let's check and review our answers. So moving on to question number 2, what is the total area enclosed by that graph and the x-axis? So if you can see, I've actually highlighted the x-axis so they can see that boundary line. I'm trying to find the area of this semicircle, the area of this triangle, and the area of this trapezoid. I like to ask my students to separate those so that they are finding the area of the semicircle, 9 pi over 2, the area of the triangle, 4, and the area of the trapezoid, 5 halves. To find that total area, we will add those all together. It's at this point that I have a discussion, if I have not already, about leaving things in terms of pi and how this is an exact answer, whereas if you were to take that 9 and multiply by 3.14, or even the pi button on your calculator, that is an estimation, that is rounding, and is an approximation of what the actual exact answer is. So for this worksheet, we're going to keep things in terms of exact numbers. If you have students where you need to scaffold that and allow them to use decimals, they may do so, but it does make a little bit of the connection not seem quite as easy to observe. For question 3, we are asked to find the line of symmetry if one happens to exist for each of those following intervals. So helping your students understand that this is not x is -3 and y is 3, but this is an interval from -3 to 3, from where x is -3 to where x is +3. I'm looking for that line of symmetry. That is going to happen here, which happens to be the equation x is equal to 0. For the next interval between 3 and 5, I have a line of symmetry here, which is the equation of the line x is equal to 4. For our remaining intervals from 5 to 9, there is no line of symmetry, and for the entire f of x graph, there is no line of symmetry. So the question 4 asks us, how does this line of symmetry affect the area of this shape? Because it is symmetrical, half is over here, half is over there. Same for the semicircle. It is being cut in half. So those areas are also being cut in half. Finally, for the first portion, we are asked to talk about the vertical line x is equal to k, and that vertical line divides the entire area into between the f of x and the x-axis into 2 equal parts. They don't need to know exactly where it is. They just want to know what shape that happens to occur within. So if we're looking at what our areas are equal to, the area of the semicircle is 9 pi over 2, which is hard for me to understand because of the pi sometimes when I'm trying to determine what half is. So if we allow our students to go in and determine what half of that is, the total area, 9 pi over 2 plus 13 over 2, is approximately 20.637. The area of the semicircle is approximately 14.137. So the semicircle is already more than half of the total area. So wherever this line is, that will occur somewhere within the semicircle. The stem of this question is something that is seen very frequently within AP Calculus. You'll notice that a lot of the terminology, a lot of this notation is the connection, it's the bridge between the geometry concepts we've asked them to learn throughout the year and where we are expecting them to go. So that is our first 5. That's the trunking that I typically do with my students. We'll pause, regroup, make sure that we all understand, and get ready to move on to number 6. So take a moment, pause your video, work 6, 7, and 8, and when you're ready to come back, we will check our answers. We are ready now to start looking at the next portion of our practice, where we are moving on to working with a transformation of our f of x function. So what we're looking at on 6 through 8 really focuses on this new function that we're defining, g of x, which is equal to negative f of x. So what we want to look at here is what that negative actually does to our function. We're hoping that our students will remember from the transformations unit that that opposite of, remember, these are y's. So if we negate our y, that we are actually reflecting that over the x-axis. So we're hoping that our students are able to visualize. If not, you may want to use some graph paper, some tracing paper. You can use multiple copies of the f of x graph printed out, but we want them to be able to recognize that what that reflection g of x will look like is something here, where everything we have for f of x just gets reflected over that x-axis. These are the new shapes that we have, the new forms that we're going to look at for g of x. G of x being just the blue part, just this portion that is reflected over, not the entire thing. Otherwise, it would not be a function. So in looking at our questions for this portion of the practice, they want us to determine that total area between g of x and the x-axis. Again, they can work through that, but our goal with this is to help our students to have a deeper understanding of the concept of area and functions and transformations and how we can use those ideas to answer some of our questions without actually having to calculate things. So in looking at the fact that a reflection is a congruent, it is a rigid transformation, then our function will be the same between the function and the x-axis, so it will have the same area as the original function. Classify each of the geometric figures formed between the two graphs. So notice that the x-axis is not involved here. We are going all the way from the top to the flipped over portion on the bottom. That means that we have an entire circle now, a rhombus, and an irregular hexagon. Irregular is a vocabulary word that the students should be familiar with. And then finally, what is the area enclosed by the graphs of f of x and g of x? So because we know that between g of x and the x-axis was 9 pi halves and plus 13 halves, and we know the same was for between the f of x function and the x-axis, if I'm now going between both of those, my total area will be twice that amount, or 9 pi plus 13, which is a much simpler, time-saving, straightforward way to think about this, rather than having to actually calculate the area of the circle, the area of the rhombus, and an area of a hexagon, which they probably are not familiar with up to this point. So that is our portion 6 through 8. What I'd like for you to do now is take some time to look at 9 through 11. Go ahead and pause the video, work through 9 through 11. When you're ready to come back and check your solutions, then go ahead and press play. We're ready to look at our solutions for 9 through 11. So in looking at 9 through 11, we are given a new function. We are given h of x is twice our original function. What is that total area between this new function that is twice as tall and the x-axis? They give a hint to you here because an ellipse is formed as to how you would actually calculate the area of that ellipse. What I'm hoping that some students will pick up on, though, is that, well, if I've my function is twice as tall, then my area will be twice as large. And I'm able to then get 9 pi plus 13. If they actually use the formula for the area of an ellipse and they figure out what each individual area is and add them together, we should still get 9 pi plus 13. For part number 10, we're hoping that if they didn't pick up on this scalar factor here in number 9, that they will now for number 10, because if my new function is 4 times my original, my total area will be 4 times the original and be 18 pi plus 26. What 11 is asking them to do is to actually compare those to the original and to state what we know. We know that if we have a factor with our original function and that a is positive, that area is just simply a dilation. It is a scalar of our original function. So at this point, we're ready to move on to the next portion of our practice, to looking at 12 and 13. So take a moment, try to work 12 through 13, pause the video, and when you're ready to check, come back. We're ready to check 12 and 13. If we're looking at 12 and 13, what they're asking us to do here is to still find that total area underneath the function f of x, but now we have different boundary lines than the x-axis. This is where, again, having tracing paper, or you could display the graph on your whiteboard and have students use dry erase markers and work this together as a whole class. We want to take a look at what that would actually look like. So if I'm looking at this graph, the lines that I'm now being bounded by is y is equal to -1, x is equal to -3, and x is equal to 9. So not only do I have the original area that we started with, but I also have this area down here on the bottom. Rather than trying to determine what the area of this entire shape is that is now no longer just a semicircle, we can decompose this into the original area that we do know and the area of this rectangle on the bottom, which is a 12 by 1. So in doing so, we can take our original area and add to that the area of the rectangle to get 9 pi halves plus 37 halves. The same can be said on 13, where I'm taking my original function and translating that up 1. Again, seeing what that visually looks like, you should be able to see that we have our original function plus the area of a 12 by 1 rectangle, giving me the same area that I had here, which is 9 pi halves plus 37 halves. So we're ready to look at the next portion of our graph. This is the final portion that we'll be looking at that starts to move away from the transformation portion and the area portion to other concepts such as increasing and decreasing and equations of our lines and equations of our functions. So this is really where the connection, again, from what the standard is in geometry to where we are expecting them to go with it. And for students, knowing where they're headed is very important, because we want them to understand that the skills that they're learning are not just something that they learn for geometry, but something that they will be expected to recall and use later, and that the learning does progress as they continue on with each of their advanced courses. So take a moment, look at 14 through 18, and when you're ready to check your solutions, press play. So we're ready to check our solutions for 14 through 18. What we're looking at the beginning of these is intervals of decreasing and increasing. So you can allow your students to use interval notation. This may be something that they are not familiar with. So if you would like your students to use more traditional notation from middle school, then they should be familiar with this sort of notation where x has to be between 0 and 3. But this is a great time to introduce that notation to them as well, and discuss the brackets being used when you have the equal to, which should be something that they are familiar with as well. So intervals of decreasing, x is between 0 and 3, between 4 and 5, and from 7 to 9, intervals of increasing, -3 to 0, 3 to 4, and 5 to 6. Another important concept that they will be required to use in pre-calculus and AP calculus is the idea of absolute maximums and minimums, and more so the idea of what they are along with where they occur, which is the difference between 16 and 17. 16 is asking your students, what is the absolute maximum? The absolute maximum or minimums are always y values. So for our f of x function, that absolute maximum y value is 4. Where that occurs is what 17 is asking us. So how many times do we have an f of x or y value of 4? And where does that happen at? Well, that happens when x is -3, 3, 5, and 9. And finally, we want to look at number 18, where we are going back to g of x being twice our original f of x. What we're hoping our students will see here is that that absolute maximum is again just a scalar. It is just being dilated. So our original absolute maximum was 4. Our new absolute maximum should be twice that much and be 8. So at this point, we're ready to start looking at number 19, writing the equations for f of x using 5 different equations. Most of our students are going to want to use 6, and that's okay, but we do want to have the discussion with them about how we can turn those 6 equations into 5. So take a moment, try to work number 19, and when we come back together, press play, and we'll check our solutions. Welcome back. We're ready to start talking about our solutions to number 19. So again, they're wanting us to use 5 different equations in order for us to write this. Most of my students typically think of 6 and realize that they don't have enough lines, and that may be something we need to discuss together as a whole class as to which of our function equations can be written together as one. So what we're wanting our students to see is, how do I write the equation of this semicircle from where x is equal to -3 to where x is equal to 3? So if we think about it in terms of a circle, then we have our center at 0, 0 with a radius of 3. So we are then able to get x squared plus y squared equals 9. However, this is f of x, not f of x and g of x. So we just need the portion that is positive, the portion that is above the x-axis. And as well, this is solved for f of x. This is being solved for y. So all of these function equations need to be solved for y. So our students need to take our equation of the circle, subtract the x squared, take the square root, and get that y is equal to plus or minus the square root of 9 minus x squared. And then we have to make the distinction that because we are only looking at the portion above the x-axis, that is the positive version of our solution. This is a great tie-in to make with the equation of a square root and the equation of the circle, and why we need that plus or minus as well. Typically, for the next portion, my students will make the equation of a line and make the equation of a line. Again, using slope-intercept is okay here, but then they have to continue on with the slope in order to get what that y-intercept is. And the same here, to continue with the slope to achieve the y-intercept. So using point-slope formula, which they did previously in other practice worksheets, would be a simpler version for them to choose to use here. However, we would love if they could pick up on the fact that that is actually an absolute value equation. That is an absolute value equation that has been translated to the right, reflected down with a slope of -4, giving us our equation that we get here. Now, for students that have not taken Algebra 1 yet, that may be a bit of a gap of information that they do not know yet, depending on how much their middle school teacher did with them when they were writing equations of lines and equations of functions. For our next portion, we have the equation y is equal to x minus 5, which we can get here because our slope is 1. And if you want the y-intercept, then you can continue down to get that y-intercept would be -5. Here, the equation of our line is y is equal to 1. And then we have the equation of our line, y is equal to 1/2 times x minus 9, which can be distributed as well. And again, using the interval notation so that we know that this particular function equation only applies for this portion of our graph. So we have two final questions, 20 and 21, that ask us to use this information. So what's great about this activity is that it is easily chunked into smaller pieces, which you can give to different groups and bring back together, or you can give to different members within the group and help them work together. And then as well, at the end, it becomes much more algebraic and allows them to focus on the algebraic side. So the beginning is very geometric and visual and dealing with area and transformations, and then it spirals in the algebra practice that they need. So it's very much an all-encompassing practice activity. So take a moment, look at 20 and 21, and when you're ready to come back and check your solutions with me, press play. We're looking now at question number 20. Question 20 says, what is x when f of x is equal to 1/2? And to justify algebraically. In order for them to justify that algebraically, that means that we need to be working with our algebra skills in order to solve for what x is. So what I always try to have my students do is to tell me what the question is asking them. The question is asking, what is x when f of x, or y, is equal to 1/2? And so now I simply have to take those 5 functions that I dealt with previously, substitute in a 1/2 for my f of x, and then I'm only left with the variable x, and I can solve for x. Students should be familiar with how to solve equations with square roots and powers of 2, as well as working with the operations within a square root function, because we dealt with that previously in the Pythagorean theorem unit. Keeping in mind, you may need to remind students again of the plus or minus that goes along with when you square root a function. For our absolute value function, this solving may be something you need to remind students of. It is a skill that they learn in middle school, but one that they tend to easily forget. So you may want to help your students remember that after you substitute in for 1/2, you isolate that absolute value. And because that absolute value is measuring the distance from 0, then we know that it is either in the positive direction or it is in the negative direction, and therefore we are going to get 2 solutions, which is again why it has that V shape. For our final 3, these are a bit simpler, so depending on how you want to scaffold this within your groups, you may give these to students that you feel need to be successful and need to be able to contribute to the group. So here we know that f of x is 1/2, and I'm able to solve for x and get that x is 5 1/2. Here, when I substitute in 1/2 for f of x, I'm given that 1/2 is equal to 1, which we know is not true. There is no variable x here for me to solve, therefore that is a no solution. There will not be an instance where f of x is equal to 1/2. And finally, substituting in 1/2, distributing and solving, we are able to get that x is equal to 8. So we have multiple solutions depending on where we are in f of x, where f of x or our y value would in fact be equal to 1/2. Finally, we get to build slope into this as well. We are looking at determining the slope of each of those points on the graph of f of x. So what we're looking at here is when x is 3.5, 3.5, we need to know that y value, and we need to know what the slope is. So our students will need to refer back to our original graph and determine that when x is equal to 3.5, what is that y value? It's 2. What is the slope of that portion of the graph? It's 4. When we're looking at something like 6.213, I don't know exactly where that is, but it's a little bit more than 6, which puts me here. Every y value here between 6 and 7 is 1, and that slope is 0. When we're looking at -3, our y value will be 0. Here we do not have a slope, because -3 is the beginning portion of that semicircle. There is no slope here because there is no defined function below or behind that -3 value. And then our remaining y values and slope functions. So I hope that you see that this is a great activity that spirals in several different points of information from geometry and algebra and middle school, and really allows our students to recall things that we're expecting them to be able to do in upcoming mathematics courses and keep all of that information that we're teaching them fresh.